So let's continue from where last lecture, where we were doing an analysis of randomized quick sort. That was a little hairy, and so that's why I'm going to sort of summarize it again. Those of you who weren't quite sure if you really got it right at the end. When we said we need to do analysis, because it was a random, it's sort of natural for us to say we're going to look at not the worst, we're going to look at the expected scenario. Okay, so we're going to look at expectations. We have randomization. We generally refer to the expected complexities rather than the worst case. The idea why are we now looking at the complexity rather than the worst case? Why not best case? Why the expected complexity? Whenever you have randomized algorithms, yes. Sorry, I was pointing at this gentleman. Okay. Yeah. It is what, sorry? It's so unlikely, yeah. So, and earlier response, could you repeat that? The gentleman in the back who initially started off? Right. So essentially, when you run, basically what we're saying is now there is a uniform distribution, which wasn't guaranteed earlier. Remember that. Examples, and I said in a lot of real world cases, the data is not necessarily distribution. Now that we do have a guarantee on the distribution of the input, we can then rely more on the expected value. And we also know now that the worst case, but it is now extremely unlikely. So if you just think about your distributions, become less and less likely if the distribution of the input to be normal, uniform. All right. So now the next thing that we did, and this was perhaps the most trickiest part, is that to be able to see what's the relationship between defining it as the total number of comparisons over all. So again, the key word is, and we'll delve a lot on that particular we go through this lecture today. So we're looking at the total number of comparisons. So comparisons essentially are the hard sorting algorithm, most sorting algorithm, except those that we'll talk about later today as well. But if you focus on the comparisons and the number of comparisons, and if you can identify what are the number of comparisons, then essentially you've hit on the essential time complexity, which we were able to show. Hopefully you got that lot. The complexity and the total number of comparisons are very closely related, and I didn't show the order in the last lecture, but you can replace that. Essentially, what we complexity is now big O or big T, the expected value of the number of comparisons. Okay. So having gotten over that and made you realize that that is true, hopefully, then essentially the problem becomes, in the randomized problem, to be able to compute the expected value of that random variable x, okay? And so we resorted to defining certain new variables, and we defined z sub I, the sorted, and we defined zij to be that subset of that sorted list, which goes from I to j. So everything in between is sorted, okay? So Z37 was, for example. Then we introduced the indicator xij, and we said, and again, this is hopefully you got that as well, that x can be written as the xij's for certain range of variables for the range of i's and j's is given. And then we essentially said that, indicator random variables have this really nice property that the expected value is simply by probability that is equal to 1, okay? And so essentially what we're saying is that the expected value of X in the case is the probability that I is compared to ZJ, okay, which is the indicator random variable, okay, that particular event occurs. So then we said, well, now we need to compute what is the probability that Z are in fact compared. Okay? Given that Zi and Zj are a subset list, and Zi is the smallest value subset, and Zj is naturally the largest value. Okay, and so this is where perhaps we sort of glossed over this in the last lecture, but let me repeat that. So Zi and Zj are compared if and only it's important if the first chosen as from Zij. So the first element to be chosen as a pivot from that entire range Zij is either Zi or Zj. Okay. So as an example, if you have Z, and this is that subset, saying that the probability that compared to 7 is 1/5, right? Well, actually, well, 2/5, but one of these is chosen as the first pivot, okay? Is, let's say, the probability that 7 as the pivot is 1/5. The probability that 3 as a pivot is 1/5 because you have 5 numbers in that range. Okay. Total probability is that either one of them that they're compared, either one of them is chosen the initial pivot. Okay, and there are two possibilities, either Zi or Zj, and so it's 2 times 1 upon this number, which is simply the number in that range from Zi to Z. Okay, so that then the rest of it is a bit of a algebraic manipulation. We do have a summation. We did some substitution of these ranges, come up with this, double check this, and then we sort of stuck over here. And the next thing what we can do is, when you sort of stuck and we're looking for an order of complexity, we try to make things simple. So we say, well, can we convert this into this? And possible if we sort of put less than sign over here, and we change the range to be a larger number. We reduce the denominator, so both using the right hand side, and so we can say now the left hand side is not equal to, but less than the right hand side. Okay? And so then we have, okay, because we're looking for a big O notation, which is upper bound, and so we can increase the right hand side. And so from the harmonic series, we know that this harmonic series log of n and of an order of 1 complexity. So that was the formal proof of of the fact that the expected value of is going to be n log quicksort. Okay, so essentially this is where we are. We've looked at 3 comparison algorithms, 3 merge sort, quicksort, and 2 versions of my internet is. Just give me a minute. Let's see why that's the case. I did switch it to my Android, and I don't know what else can I do. Okay, so if people online are having serious problems with the quality of the internet, do unmute yourself and let me know. So it impacts the quality of the recording. So we have 3 sorting algorithms, and we, just to summarize, the merge sort is clearly obviously based on merging, based on partitioning, and this is the same for and in the case of the randomized quicksort, we're not going to be looking at the worst case scenario. Rather, we're simply going to be looking at the expected. Okay, and so we do realize that quicksort did have a problem over here in the worst case scenario, and merge sort did not have that problem simply because of the way it was doing the divide and quicksort because on selecting a pivot, and that it could have problems, and that's why the worst case is order of n squared. Randomized quicksort, we overcame that problem by doing the randomization, and so the expected value n log n, and that's rather than to say that the average case is n log n, but the worst case is this. So in all, we would say that the random is the essentially more guaranteed, okay, as compared on the non-randomized. Right. So this is where we are as a certain class, and now we'll chapter 8, which looks at two things, and the first one bounds on sorting, and the second part is going to be. So let's take a look at all the algorithms and think about what is perhaps the commonality sorting algorithms that we looked at so far. Okay, can anybody sort of that we've looked at so far, and what's perhaps one common theme that exists throughout these algorithms? Yes. It's making it smaller. So you talk about divide and conquer. Okay. We have algorithms, although not directly, have come across them. For example, insertion sort. You do remember insertion sort. So, cards and looking at a number and saying, well, insert it. Okay. That wasn't really, it wasn't really a classic divide and conquer. Okay. But so if you include insertion sort and other sorting algorithms that you can think of, there's one word that I've been, sort of emphasizing in the last few minutes. Yes, comparisons. Word that I emphasized, and so comparisons are essentially one of the key elements, key aspects of all of the algorithms that we've seen so far. You might have seen some other algorithms which we have talked about, but for all that we've seen so far, comparisons, and not just comparisons between 5 numbers, but pairwise comparisons. Okay, so we're always obviously comparing 2 numbers, and we're saying, well, if this number is smaller than the other or is bigger than the other, we're going to do some sorting. Okay? So essentially, comparisons are, and then you might say, well, how can one actually do sorting without doing comparisons? Is that even possible? I mean, can one think of a way to do comparison to sorting without comparisons? Seems kind of non-intuitive and illogical, right? How can you sort without doing comparisons? Yes. Yeah. So you have some insight into this, and so from an intuitive point of view, I didn't get your name. Nishit. So Nishit has a suggestion that there's some algorithm that he's heard of. It's called bucket sort, and what that does is it takes the numbers and it sort of says, well, let's look at the range of these numbers, and we're going to put them in different buckets. Okay. So yeah, so that's the direction we're going in. But just think about from an intuitive point of view, if you want to sort a bunch of numbers, and another important thing that Nishan mentioned is that let's assume that there's a certain limit on the range of those numbers. Okay, so they're not going from 1 to infinity. Let's assume that they're going from a certain range from 1 through, let's say, some number k. Okay, it could be 100, could be a million, could be 10 power million. Okay, there's another answer. Yeah, yeah. Okay, so yeah, we've kind of going too far ahead because we haven't really talked about bucket sort, so people will get confused. So let's not talk about bucket sort yet. Okay, we will, but later on. So let's think about it in a more natural sense. I mean, can you just forget about the words bucket sort and so on? Just think intuitively. If you had a bunch of numbers and without comparing, let's say you had the numbers 1 through 100, right? And you wanted to sort them. Let's even assume that they're all distinct. Okay, each one of those numbers are different. So can you come up with an algorithm to sort them without comparing them with each other? Yes. Yeah. So that's a great thought. So what you can I get your name? Sorry, David. Okay. So David's suggestion is that you could just let's assume that the numbers are from 1 through 100. They're all distinct. So what we could do is we could just look at each number without comparing it with any other number. And we say, well, the number 5, let's put it in array location 5. Okay, so we have a new array. It has contents 1 through 100. And for each of those numbers, we're going to just pick it up and we're going to insert it into the corresponding index of the other array. Okay, yes. Yeah, so essentially, we're going back to Nishit's point, is that we're assuming there's an upper limit on the range of numbers. Okay, so your point is absolutely true. You're assuming that those numbers are limited to 1 through 100. Okay, if there was a number which was 1,000, obviously then you'd have to have an array which is of size 1,000. Okay, and you know at some point you can see the problem because we now the array that we're using for additional space has to be bounded. Okay, but that's the general idea is that you know without doing comparisons we could actually do sorting perhaps with this general idea to be able to take numbers, put them into another array, and you know just have the index of that array identify whether that number is existing or not. Okay, yeah. Yeah. So we could do something fancy. So right now we sort of doing a very intuitive analysis and trying to say, well, yeah, you could do something like that, but you can see the complexity. Okay, there could be some issues. What happens? Well, there are a whole bunch of numbers which are not present. What do you do with them? How do you make sure that you only have the numbers that you really want in the original array, right? So there are lots of complexities, and so we'll have to actually look at the specific algorithm which solves this. And we'll have to see how does that solve it. Okay. So, but before we even get to the non-comparative sorting algorithms, let's figure out whether the sorting algorithms that we've seen so far, and two of the good ones, I guess you might say the merge sort and quick sort that we've been talking a lot about in this course, they provide you some guarantees, right? So we saw that you had the following properties, you know, you had n log n always appearing. So this magical, term n log n is appearing all over the place. And so the question is, can we do better than that if we are limited to certain class of algorithms? Okay, so let's assume that we're still working with algorithms which are doing comparisons. Okay, we forget for a moment what we just spoke about, which are non-comparative algorithms, because we'll take a look at them later on. Let's assume that we're only taking a look at comparative algorithms, algorithms which compare two numbers pairwise. Okay, or is this the best that we can do? And can we do something even better? For example, can we do n log of n? Right? That would be better than n log n, right? Or can we just do n? Linear time, right? So, so now it brings us to the issue of can we bound? If you are doing a comparison-based sorting algorithm, can we bound the expected value, or can we bound the worst case? Okay, so let's take a look at how one could do that. and see what we get. Okay. So we're going to focus for the next, for a short while, just on comparison-based algorithms, and they're going to be called comparison sorts. So we're going to use a decision tree model, okay? And the decision tree works as follows. So let's assume that we just have 3 numbers that we're working with, okay? So n is equal to 3. And we're trying to say, well, what is the minimum number of comparisons? Because again, comparisons are key, okay? If we can figure out certain bounds on the number of comparisons, then we can have bounds on, you know, the expected value or the worst case, okay? So let's take a look at, and the algorithm could be the randomized or non-randomized, okay? So let's take a look at the following decision tree. And we're going to use the following notation. We're going to say, well, at the end of the decision tree, we have all the possible ways in which you could have the answer. Okay, so these are the leaves which are shown in purple. So you could either have, you know, there are 3 numbers, which could be 10, 20, and 15. Then clearly, in this particular case, the sorting order is 10, 15, 20, which means that A1 and then A3 and A2. Okay, so A1 comes in first, and then A3, which is 15, and then A2. So that's the, in this particular case, if you choose the numbers 10, 20, and 15, you need to come up to this particular leaf in the decision tree, okay? But there could be, of course, how many other possible you know, solutions. Clearly, it's going to be, if you have 3, it's going to be 3 factorial. If it's going to be n, there are a total of n possible ways in which you could permute, you know, you could permute all of those. And so you have n factorial over here, okay? Permutation of n. So how do we get to those leaves? So let's take a look at the number of comparisons, okay? So so in this case, we could start off, let's say, comparing A1 and A2. Doesn't have to be the case. You could have different types of decision trees. You could start off with comparing A2 and A3, okay? So let's say that this is one possible decision tree, and we're going to start off by comparing A1 and A2, okay? And if A1 is less than or equal to A2, we're going to go in this direction. If it's greater than, we're going to go in this direction, okay? So that's one comparison. And then we're going to have, let's say, we need to, well, we've compared A1 and A2, okay? Then clearly we're not at the end. We can't really decide the order unless we compare these 2 numbers as well, okay? So you could have A2 and A3 compared, depending on whether it's less than or greater than, you go in one of these directions. Now, if 2 is less than 3, you've already got to the leaf. Why is that? Because A1 was less than A2, let's assume, okay? And then A2 was less than A3. So in just 2 comparisons, we've actually been able to sort these numbers. But that doesn't have to be the case. So what if A1 is less than A2, but A2 is greater than A3, okay? So A1 is less than A2 and A3, so A1 is less than A2 and A2 is not less than, so A1, now we're saying A1 is less than A3, okay? So you've got these 2 results, and so we don't really know how A1 and, so we've got A1, A2, okay, and we've got A1, A3, but we don't really know how A2 and A3 compare, okay? So in some cases, you may have a smaller number of comparisons. In some cases, you may have a larger number of comparisons. So you could end up at a leaf with just 2 comparisons. You may end up at the leaf with 3 comparisons. Okay, and you can sort of figure this out. This 2 case is the one which only requires 2 comparisons. And these are cases which will require 3 comparisons. But it depends on the decision tree that you come up with. As I said, that you don't have to start with A2 and A1 and A2. You could start with A2 and A3. That could be a separate. But the point is, the bottom line of showing this is that if you look at, you eventually have to get to one of the leaves. All right. So the question is, it's clear that the number of leaves is going to be n factorial. Okay, is everybody clear on that? Because there's n factorial ways to permute these n numbers, right? So we have to get to these leaves. And the way to get to these leaves is go through the decision tree. And the decision tree essentially is saying how many comparisons are you making. So at every stage in the decision tree, we're doing a comparison of two numbers. Okay. So if you want to get the order of complexity, what do we need? How could we put a bound on the order of complexity given this notion of a decision tree? Think about the tree has different properties. It has leaves. It has a certain number of leaves. It has total number of nodes, which are n. It has height as well. Okay. So can you sort of start thinking as to how one would actually get a bound on the number of comparisons? And I've already given you sufficient hints as to what are the number of comparisons are you making? Somebody else as well. So think about how many comparisons are you making as you go down? What does it relate to? Does it relate to n, the number in the tree, the number of nodes in the tree? Does it relate to the number of leaves in the tree? Does it relate to the height of the tree? What does it relate to? What is the number of comparisons, the worst number of comparisons relate to? Okay, I'll give you. Yes. The height. Okay. So was that your answer as well? Yeah. So as you can see that the height is essentially telling you what's the worst case number of comparisons. Okay. So the height is telling you the worst case number of comparisons. And if you can somehow put a bound on the height of this decision tree, then you've got a bound on the number of comparisons. Okay, so we could look at the worst case, or what's the worst height, and what's the best case. Okay, and essentially what we're really trying to do is we're trying to say, well, merge sort and quick sort had an n log n worst case. Okay, so we're trying to say, well, is n log n, can you do better than that? And in order to be able to do better than that, what would we have to prove? What would we have to prove about the height? You're trying to prove that n log n, for instance, so n log n, we just found the best solution, merge sort, quick sorts are the best simply because both of them are giving you n log n. And we're trying to say, well, n log n is, you just can't do better than that. What do we have to prove? Yeah. That the height is less than log of n, which you're sort of doing the counter. Saying that if the height is less than n log n, then you're saying the number of decisions can be, in the worst case, can be less than n log n. And so then you can have a better algorithm than merge sort and quick sort because those guys are doing worst case analysis in n log n. So the height, you're almost there, but perhaps you have the inequality on the other side. So you're saying the height has to be less than n log n. What I'm saying is that it should be greater than. Okay, so if you can prove that the height is always going to be more than n log n, then in the worst case, then we're essentially saying that the number of comparisons that you have to make is going to be greater than n log n. Okay, so in that case, we could say, well, merge sort and quick sort are, in fact, you can't do better than that if you're doing comparison based, because this is all based on comparisons, right? So if you can put, if you can say that h is always greater than or equal to n log n, okay, then we found a lower bound on the complexity of sorting algorithms. Would you agree to that? Okay, so we just have to find a lower bound on the height. Now, a tree, right? I'm not saying if it's what kind of a tree is it. We just say, let's say we have a general tree, and we know that the number of leaves that it has is n factorial, right? So if you have n numbers that you want to sort, then the number of leaves is n factorial. Is, by the way, n factorial a big number or small number? How does it, do you have some idea what n factorial is? I mean, in terms of complexity, can you represent it as some other expression? Yeah. Yeah. Yeah, so say that again, the last part. So can you sort of give an expression for, is it Is it like n squared? Is it n cubed? Is it n to the power 100? How does it, what is n factorial like? Yeah, so forget the constants, okay? In this course, we're going to forget about the constants. So look at the big picture. You said it's n to the n times some constant, maybe divided by something, to the power of n. I mean, that's a big number, okay? In terms of complexity, that's what as bad as you can get. If you have an algorithm which has a complexity of n factorial, that's, you know, that's one of those NP-hard problems, okay, if you've heard of those. So n factorial is a really large number, simply because it doesn't seem like it, but because you're doing n times n minus 1 and you're going all the way up to 1, that number is actually n to the power of n. No, you go up to 100, that's 100 to the power of 100, right? You can imagine the complexity of this universe. It goes from, I think, 10 to the power of minus 40 to 10 to the power plus 40. That's the entire range of this entire universe. And all of a sudden, if you're saying 100 to the power of 100, that's, you know, I mean, you can't even, you can't even imagine those numbers. So n factorial is an extremely large number, and any algorithm which has that sort of complexity is just doomed, all right? So if you have leaves which are n factorial, can you now sort of intuitively tell me, and now we know that n factorial is something n to the power n, okay? Sort of like that, and some constants associated. So now, if the number of leaves is that big, and you're looking for the height, now what are the property of this tree? I said this is a general tree, but is that really true? If you have a pairwise comparison, what kind of a tree is this going to be? It's a, somebody said that? Binary tree, right? So can I get your name, sorry? Valerie? Madeline, okay, sorry. I'm kind of hard of hearing sometimes. So, so as Madeline said, this is a binary tree. Why is that? Because clearly you're doing pairwise comparisons, because at every stage you're making a binary decision, okay? In some cases, you know, in all cases, every decision results in either going in the left direction or the right. You don't have, you know, three-way comparisons. So you can't really do that in most cases. So all comparison-based sorts result in a binary decision tree. Now, so now I've given you certain restrictions. So the tree is the binary tree. The number of leaves is extremely large, is n factorial. Okay. Can you put some kind of constraints on the height of this tree? What do you think? What's the minimum size of the height of this tree is going to be? Can you think of an intuitive response to that? This is n to the power n, okay, the number of leaves. And you're making, you have a binary tree, but is it binary tree always, is this a full tree always? So do people remember what a full tree is, full binary tree? What is that? Can you define that? Except for the leaves, yeah. So essentially, it's almost symmetric. It goes all the way down to the bottom. Okay, is this a full tree? No, because some of these leaves are actually at different levels. Okay, so if all the leaves are right at the bottom, and you have, so if binary tree would be going something like this, okay, or it would keep on going like that. It's not going to end in the middle. So sorry, a full tree. So this particular decision tree doesn't have to be a full tree, could be, doesn't have to be, okay? But let's take the worst case, the two different scenarios, and try to see, well, if it was a full tree, okay? If it was a full tree, what's the relationship between the height and the number of leaves? Okay, what's the relationship between the height, h, and the number of leaves? All right, so I'm not saying the leaves are n to the power n factorial. I'm just saying, what's the relationship between any full tree, the L and H? It's full binary tree. Should be sort of kind of obvious by now. Yes. Yeah, so H is going to be something like this, right? perhaps log of L, or it could be log of N. Either way, it sort of is in the general direction, right? So in other words, the number of leaves is going to keep on doubling, right? So it's going 2, 4, 8, and 16, and so on. So clearly, the number of leaves in a full tree are going to keep on doubling, and so there is a log relationship between the height and L. Okay, so that's one relationship. And so we're sort of saying that if we know what n factorial is, okay, from Stirling's equation, and we know what the relationship between H and L is. So this was a case where it was a full tree. Now, what happens if the tree is not full? Does the height go up or go down? As compared to the relationship between H and L, if it's not a full tree, as in this particular case, does the H become larger or does it become smaller? It becomes larger, right? So because you can see that if it's sort of going in this direction, it's completely lopsided binary tree. And clearly the number of leaves is still 1, but H is becoming larger and larger. Okay. This relationship puts a lower bound. If you know what L is, then you can get a lower bound on H, assuming that it's going to be a full tree. Okay, so you can assume that this is a full tree, and you can say, well, H has to be at a minimum given by a certain relationship, and H can only become bigger if the tree is not full. Okay, so hopefully getting the general idea. So now we are sort of looking at the number of leaves. We can actually get a lower bound on H. Okay, assuming that and we can get a lower bound, and then in the worst case, H will only become bigger and bigger as compared to the number of leaves. Let's take a look at a few examples. So here's a case where you have a full tree. All right. So there you can see that the exact relationship is 2 to the power H is equal to L. So the number of leaves is exactly equal to the power 3. All right. Comes as no surprise so far. If it is not a full tree, then you can see that H is going to be bigger. Okay, so H is going to be bigger. The number of leaves in this case is only 5, right? So 1, 2, 3, 4, 5. So you can see that 2 power H is now greater than equal to the number of leaves. All right. So now we've got one relationship between L and H. So if you go back, are we making progress? So you've got a relationship between the number of leaves and the height. And the height is basically telling us how many decisions are we going to make. Okay. So so keep going forward. What else do we need? That's one relationship. We've sort of got a relationship between L and H. Okay, and we've got a lower bound on H. Okay. What else do we need to be able to come up with a decision? Okay. Now, what we can do now is plug in the value of L in terms of N from Stirling's approximation. Okay. So we already know what L is. That's given by something which is extremely large, n to the power n. And we've got L, a relationship between H and L. We just need to plug in the numbers, and we should be able to get a lower bound on H. Okay, if you just follow that thought process. Okay, so let's just do that. We've got in the binary case, in the case where the tree is not full, you've got the following relationship, and essentially we've got the following relationship as we've got L. Now, this may not be completely obvious to you that the number of leaves is not just equal to n factorial, but it could, in a decision tree, it could actually be greater than n factorial. And can you think of a scenario where decision tree has more than n factorial leaves? In other words, you have maybe a poor decision tree. All right, you're saying, well, I need just, one of these two cases. It's A1, A2, or it's going to be A2 and A1. All right. So let's just think of two numbers. So this clearly, if you just have two numbers, there's only clearly two leaves. But let's say you have a really bad decision tree. You have some MBAs working on this decision tree, and they're coming up with these strange algorithms. They don't know math at all. And so they're coming up with third scenarios, and you're saying, here's another possibility, great. And this one also says it's A1, A2, right? So you've got the number of leaves, it can actually be greater than or equal to n factorial. And there may be some duplicates. Okay, so these two are duplicates. So that's why generally for decision trees, keeping some flexibility for our MBA folks, they have 4 decision trees, and so you could have the number of leaves could actually be greater than n factorial. Okay. So if you have these two scenarios, then clearly n factorial is less than. So this we're just going to replace this the other way. So n factorial is less than the number of leaves, which is less than to the power h. Okay, in other words, n factorial is less than or equal to the power h, right? So from here now, can we get a lower bound on h? Is the rest just math? Yeah, I mean, we know what n factorial is from Stirling's formula. So now we should be able to just grind out the math, and we should be able to find a solution. And that's essentially what is done over here. We've got n factorial is less than or equal to. Okay, in other words, we want h to be greater than or equal to log of, we taking logs on both sides. So remember, whenever we have these relationships which are in exponents, a good way to compare them is to just take logs and keep on taking logs until things become simple. I think in one of the assignment questions that was suggested. So you take logs on both sides. Okay, so you have h, take logs on both of these. So you have h is going to be greater than equal to log of n factorial. And this is from Stirling's equation, and you can disregard constants over here. And so because this is a greater than equal to sign, now you have an upper bound on h. Okay, so h is going to be greater than n log n. Okay. So Stirling's formula came in real handy, and that was able to give us the lower bound. And essentially what this is saying is that if you have a comparison sort, then you can't do better than n log n. Okay, merge sort, quick sort, those have done a fantastic job. You can't do better than that. Okay, but of course, we know that there are techniques for doing better than n log n, and we've also already hinted at that. And those are non-comparison sorting algorithms. Okay, so now let's take a look at some of those non-comparison sorting algorithms. So let's start with the following. As we said earlier, we're going to make an assumption that the range of values is limited to some upper limit. Okay, that's one of the inherent problems with these non-sorting algorithms, is that we're going to assume that that range is up to a certain value. We're going to identify that with a k. Okay, so k, as I said, could be 100, it could be 10 to the power 100. Okay, but the bigger k is more problematic are the non-comparison sorting algorithms. All right, so let's assume that we start off with the following numbers, and let's, for the sake of simplicity, we're going to start off assuming that they're all distinct. Okay, and they're starting from 1. To make our life simple, 1 through k. And I've just given you an example of this. Okay, so let's say that k is equal to n, the range of numbers, n is 8. Okay, and k is given by, so this is not a good example, but k in this case is also given by a range which is 9. Okay, so the question is, can you, we already had some suggestions. Can you just find a simple solution that was earlier given? Yeah. So you could call it a bucket sort, but that's not really how bucket sort is defined. So we'll just call it our own algorithm. All right. 550 algorithm that we'll come up with. And we're saying we're just going to drop this in the appropriate slot. So 2 goes here, 5 goes here, because they're all distinct. So you don't have the problem that you have multiple numbers in the same bucket, so to speak. I'm just simplifying it. 7 goes over here, and so on. Okay. So you could do this in, what's the time complexity of this algorithm? O of n. Is that right? Mega of n. So let's just talk about O of n. All right. There are 2 numbers now. So n are the number of numbers to be sorted, and k is a range. Okay. In this particular case, we're assuming that the output is over here. Okay. And this may not be the best algorithm to look at, but you get an idea that it's sort of like looking like an algorithm which does the sorting in linear time. Okay, but I'm not going to spend too much time on this because this is something that I just made up. All right. So let's take a look at, but you get the general idea that you could simply take those numbers and you could put them into certain buckets, and the amount of time could be maybe order of n, maybe order of k, maybe some summation of those 2. Okay. So and you could use, for example, b of a of I to be able to do the actual putting the numbers into the right spot. So now we're going to look at a slightly more formal algorithm, which is called counting sort, which is based on the same idea. Okay. And there are some differences between what I just said and the counting sort, where we're saying we're going to start from 0, because we're also going to include 0. And we're going to go up to k. The input a has a size of n. Okay. But the range of numbers are going from 0 to k. So k could be a lot larger, it could be smaller than n, it could be larger. Okay. And the output we want is to be in another, it could be in place, as you call it. In place algorithms basically say you don't need to use any additional space. Okay. In place algorithms don't use additional space, and they simply take the original array, and they somehow are able to sort it within that same array. They don't take additional space. But let's assume that we are not doing an in-place sorting, and we putting the output in a separate array, which is also going to be of the same size, naturally, because we want numbers to be sorted. Okay, and we're not doing it in place. Okay. And we're going to use some additional storage as well. So unfortunately, the counting sort is not the best in terms of space. Okay, so we're using additional space. So let's start with this, and we're also allowing duplicates. Okay. So for example, here is an example from the book, I believe. So you have the numbers from 0 to 5. Okay, so here in this case, k is equal to 5, because you can see that numbers are going from 0 till 5. And you've got some of these numbers which are repeated. So 2 is repeated, 3 is repeated thrice, 0 is repeated twice. Okay. So the question is, how does one go ahead and do this sorting? Okay. So here's the algorithm, and we're going to start off with looking at a portion of it. So the algorithm says, well, we're going to start off by initializing the auxiliary array, C. Okay. And what did we see about the auxiliary array, which is going to be of size k, from 0 to k, so it's actually k plus 1. All right. So can somebody tell me, after we've done the initialization, what would the following 2 lines accomplish? So we're going from, or j is equal to 1 to n, all right? And we're executing statement number 5. So what's going to happen after we execute line 5? So what are we doing? We're going into, so let's start with j is equal to 1, right? So we're going from j is equal to 1. Let's do the first step. We're going to take a of j. Okay, that's number 2. And then we're going to take c of 2. Okay. and we're going to increment it. Right, so we're going to put C of 2, which was initially 0. So we're going here and we're incrementing it, and that becomes 1. All right. So far, so good. Next, what's the next step going to be? Yes. Yeah. Yeah. So we're going to have 1 over here, and you get the general idea. So essentially, basically, what we're saying is that at the end of this, C sub I should now contain the number of elements equal to I. Okay, so what should that be? Well, basically what we're saying is that there are 2 zeros, okay? And there are 0 ones, there are 2 twos, right? 2, 2, and there are 3 threes, 3, 3, and 3 threes. There are 0 fours, and there's 1 5. Okay, where's the 5? Here's the 5. Right, so basically you can think of this as what does this remind you from probability? What does this look like to you? If you have these numbers, is there a name for this in probability theory? Yeah. Histogram, yeah, or a distribution, probability density, PDF, or it could be called a probability mass function or a histogram, you know, there. So essentially what we're saying is that, you know, this is, it's sort of giving you the distribution of the numbers. Okay. Now, having achieved this, the question is, can we sort these numbers now? Do we even need to go through the rest of the algorithm? Can we think of a way to now to sort these numbers? Yes. Yeah, you've got the right idea. Can you get your name, sorry? Arath? Okay. Arath? Yeah. Okay, at the end or at the beginning? At the end. Okay, right. So Arath basically said that you sort of get the general idea that you look at, well, you're saying that there are 2 zeros. Naturally, you're going to put these 2 zeros over here. All right. And then there are 0 ones, and then there are 2 twos. So we put these 2 over here, and then there are 3 threes. And there's 1 5, that's it. Quite simple, right? But unfortunately, the counting sort is a little bit more complex. And I don't know why. So the reason is that it also wants to do something in addition. It wants to do stability, right? So what is, can somebody tell me what is a stable sorting algorithm? How do you define stability? Yes. Yeah. So we're assuming that these twos are not identical, right? So let's say you have there's a 2 over here and there's a 2 over here, but they're not the same. Essentially because they could represent, for example, they represent entire records of UNC students, and these are the PIDs, but the PIDs are unique. So let's assume that they represent ages. I know there are not 2-year-olds here, but let's assume that these represent, you know, ages or grades or something. And there is a difference between 2 and 2 prime because these correspond to different students. Okay. And when you are sorting them, you want to keep their relative positions. Okay. You don't want 2 prime to come over here. And once you're done with the sorting, you want B to have, you don't want B to have a property such that 2 prime is coming in before 2. Okay. In other words, you want to keep the original relative order, right? So there are 3 threes over here, 3 prime, 3 double prime. And so you want the first one to be first, the second one to be second, and the third one to be third. Okay. That's simply what a stable sorting algorithm guarantees. So you want to have a stable sorting algorithm. So we're going to have a little bit more complexity in our counting sort. So how do we achieve that? Well, we now first go from histogram to what might be referred to as a cumulative distribution. Okay, so instead of just saying that we're going to have the distribution, we're going to have a cumulative distribution. Okay, so you can see that that's all that's being done, lines 7 through 8. We're simply saying, well, we'll take 2 over here, right? That goes 2, but now we're going to be incrementing this. So we're going to have 2 here, which basically means that Ci now contains the number of elements less than or equal to I. Okay, these are just steps that we're going to follow to make sure that we understand the algorithm. So this is what we're going to get. We're going to have 2, and then the total of 2 elements less than or equal to 1. Okay, there are a total of 4 elements which are less than or equal to 2, and so on. And eventually we get to 8, which is there are a total of 8 elements which are less than or equal to 5. Okay, so we've now got a cumulative distribution. How does that help? We'll see that as we go forward. So now a slightly more complex part of the counting sort. So we're going to do the following. For j is equal to n, and now we're going to go in the reverse direction. Okay, so we're going downwards, and we're going through a double indexing. So we're going to get a of j, right? So we're starting off over here. So j is equal to 8, right? J is going from n, which is 8. We're going downwards. So we start off at the highest value of the A array, okay? And we use this to get the index of C, okay? So the index of C corresponding to 3 to 3 is right here. So we get the number 7, and we take B and we set B of 7 to be equal to A of j. So we take this number 3 and we now put it right over here, if I'm doing this right. Okay, so yeah. So, and I'm going to differentiate between the different primes. So as you can see, the first iteration of the lines 10 to 11 will result in 3 double prime going into this particular slot. Okay, can people see that? And now we're also going to decrement the value of C. So earlier C, yeah, so we'll get to that. So can somebody tell me the next iteration, what is that going to do? Okay, so in the first iteration, we copied 3 double prime right here. What's going to happen in the next iteration? Now we're decrementing j. So j is now going to be equal to 7. All right. What is that going to result in? Can somebody go through that double indexing, figure that out? Where do you think? So we're putting the numbers, we're pulling out the numbers from A, and we're putting them into B, which is our final destination. But somehow we're using this cumulative distribution function, which was C, to be able to put those numbers in the right spot. Okay. So where should 0 prime go? So we're going to look up C of 0, and that gives us 2. So hopefully it should come over here. Is that right? Yeah, I think I got that right. So do you see what's happening? And what exactly are we saying over here? So the one thing that we're also doing is we're decrementing the value of C. Okay. So I think I missed that in my analysis, but we're going to be decrementing the values as well. Okay. So essentially what we're doing is we're pulling out the numbers from A, and we're putting them into B in the corresponding locations. Okay. So after the third iteration, what you'll see is that this 3 single prime is going to go into which location? So we're going to go into C of 3. Okay. Now we've actually supposed to have decremented that. Okay, that step was left out. So this should have become 6. And now we're going to place it in this particular location. Okay, so 3 single prime comes over here. All right. So you can sort of see how the algorithm is actually taking place. All right. And the decrementing is essentially ensuring that we're able to put the numbers into the right location in B, okay? Because you can't put it in the same, we're not using bucket sort. In other words, we don't have two numbers going to the same location. We're decrementing the location where they're supposed to go, okay? And that's why we have this particular statement over here, which ensures that if you have duplicate values, they're decremented. But the real important thing is that we're doing a stable sort, okay? We're going downwards from here. And notice that each of these are going in the right relative order. 3 double prime is going in first, and then you're decrementing the value of the index. And so 3 single prime is going into a value next to it on the lower side, okay? So if you follow this train of thought, what you'll eventually see is something like this, that you have 0, 0 prime, all right? So these two numbers are in the relative right order, 2 and 2 prime, 3 and 3 prime, and then 3 double prime, and then 5, okay? So you should be able to convince yourself that the counting sort algorithm, as given over here, is actually resulting in a stable sort, okay? The right relative order. And that's going to be useful as we use this algorithm in other sorting algorithms. So the next question is, how good is it? What's the complexity? Okay, so can somebody take a look at this algorithm, tell me what the complexity is? And earlier somebody said, well, you could perhaps do it in the order of n, but maybe if you look at this, you might be able to say, well, maybe it's not exactly n. Yes, send it back. N plus log n plus k, okay? So n plus k is what your, yeah, you can just look at the algorithm and you can see that that is in fact true, okay? So if you look at this, you essentially have several loops. It's fairly straightforward algorithm, yeah. Yeah, so if k is, let's say, n squared, then you can neglect n, okay? If k is also equal to n, then it becomes 2n. In that case, you can neglect 2, it becomes order of n. So whichever is bigger, but let's say k is 1,000,000, sorry, n is 1,000,000 and k is 100, okay? Then you can neglect k. So it depends on, and that's why you add the two numbers together so that, you know, and because they're sort of unrelated, they're independent variables. So then you can determine the complexity based on, you know, do the final analysis, take a look at the actual values, and then decide what the actual complexity is. Okay. So you can see that all of these are straightforward loops. Okay. So this is going from 0 to k. This is going 1 to n. This is going to k. This is going up, down from n to 1. Okay. So each one of these is either k or it's n, okay? So you had it absolutely right. It is simply order of n plus k, or you can say big theta of n plus k, okay? Sometimes for simplicity, we simply write big O. So this is a nice algorithm. If k happens to be order of n, then you've got a linear sorting algorithm, right? It can actually do it in not n log n, but simply in order of n. However, does k have to be you know, order of n? And if you have, let's say, a number, you know, n is 100 numbers, what could be the range? What could be k? Is there a limit on k? No? Yeah. What's the upper limit on k? What's the upper limit on k for typical numbers? When you have a bunch of numbers, are we assuming that there is an upper limit on the value, the range of k? And if so, what are we assuming? Yes? Well, I'm just saying you have a bunch of numbers, right? And I'm giving you those numbers as integers. So let's say that those are normal integers in Java. So what's the upper limit on an integer? The max, right? And what would that be? There's a Java function which gives you that. You can say short and dot max value, but what does that actually give you? To the power number of bits, right? And if it's 4 bytes, then it's to the power 32 minus 1, right? So if n is your typical number, then k could be actually extremely large, right? K could be, if you have a long as your long integer, then it could be to the power 64, roughly. So k could be extremely large. So what have we achieved? Doesn't look like we achieved much, simply because we're saying it's order of n plus k, but there is no real upper limit on k, because k could be as big as to the power the number of bits, okay? And the number of bits has a relationship with n, but still it could be quite big, right? So b could be 64 bits, and 2 power 64 is quite a large number. So have we achieved anything real in terms of using counting sort, and what? Yeah. Yeah, so that's a good point. So Carl just said that it would be useful if somehow you can apply it to those cases where k is the size of n, okay? And the question is, can we do that, right? I mean, how many sorting algorithms do you know that actually do that? But there's another way of looking at it. Remember, we said that you could mix and match. You could have a hybrid sorting algorithm, which basically says, well, if you can start with merge sort or quick sort, and when it becomes really small, okay, then you can apply an algorithm which is appropriate for that size, okay? And so that it could be useful in that particular scenario, that you start with a big number, you bring it down, but that's fine. But that really limits the applicability of counting sort, okay? But what if I were to tell you that it can actually be used in more general settings, okay? It can be, depending on how you actually structure your problem. Can you think of a way that if you have an arbitrary number, okay, can you somehow break it up without using merge sort or quick sort, maybe a simpler sorting algorithm, and to be able to use the limit of k, all right? So sort of have to think about it, and we do have a few minutes, so let's look at an algorithm which doesn't do that, okay? It's not immediately obvious. So we looked at the complexity, and we found the time complexity, and as I said, if k is order of n, then it becomes order of n. If that's not the case, then you have to take into account k, it's stable. What's the space complexity before we go on? As I said, it's not an in-place algorithm, right? An in-place algorithm, essentially the amount of space would be constant. Because whenever we talk about space complexity, as I said, you're looking at the additional space that the algorithm is using. You don't normally include the actual input. Okay, so if it were an in-place algorithm, the amount of space, the space complexity would be order of constant. But is this in place? Is this in place? Are you using additional space? Clearly you are. You're using B and C. And so how much space is B and C going to be using? Remember the size of B and C? Well, one of them was K and the other one was size N. So you can see that it's going to be N plus K. Okay, so the space complexity is not perfect. But one thing that obviously should be hopefully apparent in all of this discussion is that no comparisons were actually made. Okay, we didn't really make any comparisons between any two pairwise elements to be able to figure out the sorting order. No comparisons at all. Okay. So we've been able to find a sorting algorithm which is based on non-comparison sorting algorithm, which could be considered to be linear in time, depending on the value, the range of k. And so, as I said, depending on the number of bits you're using to represent the numbers, this could be really bad or really good. Okay, so if you're just using 4-bit numbers, it's to the power 4. If you're using 32-bit or 64-bit numbers, k is really big. Okay, so that becomes very useful. Okay, so for really small values, you could use it. You could use a counting sort. But let's take a look at another algorithm, which actually builds up on counting sort and sort of generalizes it. Okay, And this is a really, it's a really old algorithm, but it's also a really neat algorithm. Okay. This is an algorithm which was actually used, it's perhaps the oldest algorithm. It actually gave rise to, believe it or not, to IBM. Okay. So the gentleman, Herman Hollerith, who came up with this algorithm, did that in the 1880s. He started the company and then that converted into IBM. All right. And the main contribution to IBM's success was Hollerith's radix sort algorithm. Okay. And this was, it was extremely useful, it's extremely relevant in doing census for a long time. Okay. And that's why IBM still is around. So it utilizes a stable linearly sorting algorithm. Okay, so and that's where counting sort comes in because it's both stable and it's linear, depending on what case. Okay, so the idea behind, I guess you some indication that the kind of like the batteries are dying. Okay, so I'll just speak louder. So the radix sort and the term radix comes in from the base. Okay, so this is a base 10, so you can think that the radix is 10. All right, and you can define any number, any decimal number to be in converted into 3 digits. All right, so you have the least significant digit, you have the most significant digit, and you have the one in the middle. All right, so if you think about the following number, if you can divide up any decimal number into different digits. Now, what can you say about each one of these digits? All right, so if you look at just the first digit, the least significant digit, what's the range of K? What's the range of values? We're talking about decimal numbers, so clearly you have 10 numbers, so it goes from 0 to 9, all right? So essentially, this can give you an idea that now if somehow you can divide up your numbers into individual sorting, sort of like bucket sort algorithms, in which what you can do is let's sort based on either the least significant digit or the most significant digit first. And that can be done in order of n plus k time. Okay, n could be very large, so n is basically the number of numbers over here, but k now is equal to 10. Okay, you've got an upper limit on k, and now you can do a sort based on either the most significant digit or the least significant digit in time, n plus k, and that basically means order of n. So you've got a linearly sorting algorithm, but the issue is, does this really achieve anything? What if we can somehow either sort by the most significant digit or the least significant digit? Will that help us in sorting the entire number? Okay, so just some thoughts. And which way would you go? Would you start with the least significant digit sorting, or would you start with the most significant? And we'll end on that, but yeah. Okay. Okay, so just stop for 1 second. The suggestion is going with the most significant digit. All right, and that seems quite logical, but let's stop over here and we'll come back after the midterm.